Okay, so we'll start the next lecture, but before we start, at the end of the day today, there'll be a session where we'll discuss the perimeter program and the program at CUNY Princeton. So that will be at 6, and then after that, there's a dinner, which is, it's halfway to the hotel. It's trivial to get there by metro, so we'll give you instructions later. But you can all leave from here just after the discussion session. Okay, so it's a pleasure to have David Schwab from this new CUNY Princeton Center, and he's going to talk about, I guess, physics applications in biology.
Yeah. Thanks so much. Yeah, so I'll be telling you about the kinds of things that you can do as a physicist thinking about biology, just so I get a better sense of you guys a little bit. How many of you have taken a course in biology ever? Oh, very low. Good. It's better that way. How many of you are skeptical of the idea that that theoretical ideas are useful in biology? More than have taken a course in biology. Interesting. Okay. So there are many different approaches that people take and have taken throughout the years, applying ideas from physics to biology. Actually, maybe for those of you that have taken a course, could someone name for me, what comes to mind? What's the most important sort of biological discovery of the 20th century? DNA. Interesting. So does anyone know that Crick was a physicist, and without physics we couldn't have done the work that he did? Okay. That's an example where tools from physics are used to probe biological systems, and there's a lot of work and a long tradition of using tools and studying the actual physical properties of biological systems. There's a more recent approach which takes the sort of theoretical perspectives from physics, but isn't explicitly looking at the physics of biological systems. And I intend in the 3 lectures that I'll give you to have a little bit of both. Today I'll give you an example of work that is actually physical, and then we'll move on to increasingly abstract things where people are searching for sort of theoretical principles that are not themselves some least action principle explicitly. It's not an explicitly physical principle, but something else that biology might be trying to do. And in fact, a lot of the exciting work going on today is of that flavor. I was having trouble articulating this, and an eminent physicist came into my office one day wondering what I do in physics, and he said, "Oh, so do you work in statistical physics?" And I said, "Yes, I do." And he said, "But do you use it the way Boltzmann originally intended?" And I said, "No," and that's a perfect way to describe the kinds of things that I do. So by the end of these three lectures, I'll show you something about how to use statistical physics not the way Boltzmann originally intended. But today I want to start with something very very concrete, and the sort of theme of today's lecture is thinking about what energy can buy you in biological systems. So you look around, you open a textbook, and you see that ATP is being used, and you had to eat food to get that ATP. Why is it being used? What's the point of it? And there are a number of sort of isolated examples that I think start to fall into general principles of the utility of energy in biology, and it also allows us to think about networks of interacting proteins that do various things that, if you don't have a theoretical perspective, just look like a random collection of proteins binding to each other. But when you think about what the system is trying to do, and maybe it makes a little bit more sense. So Actually, maybe I should see whether people have heard of this before. So the first thing I'm going to talk about is something called kinetic proofreading. Has anyone heard of this before? Okay, good. They have. So the idea is that basically everywhere in biology, proteins need to bind together to do various things, and they need to recognize each other. And they need to do it in a way that they recognize the right things and they don't recognize the wrong things, right? So maybe I'll start over here instead of there. I'm not going to introduce to you what proteins are, what DNA is, or whatever. I'm just going to start using the word, and if you're unhappy with that, we can step back. But I want to give you as little biology as possible and just give you a flavor of the kinds of things that that people do. So proteins need to recognize things, and that could be other proteins, it could be parts of DNA, whatever. So let's say they need to recognize targets. And they need to avoid false targets. So one of the things that is happening all the time in every cell of your body is the DNA is you'll have a gene on your DNA, and you need to convert it into a protein. The first step, you take the DNA. Is this coming in and out? Okay, maybe I'll move it a little bit closer. So you take the piece of the DNA that you want to convert into a protein. You make a little of it. Tell me if this is a problem. And then from that little copy of it, you so let's say we have a little copy, and it has some letters on it, and there are these other proteins that are looking for little 3-letter sequences. And what they do is there's a specific letter sequence on here, and they're looking for a compatible sequence here. And if it matches, it binds, and then the thing on the other end can come off and get attached to a polymer that creates a protein that we then use. So the ultimate challenge is so that the correct one of these molecules comes and binds where it should, and then another protein can come and take this piece and turn it into the right polymer chain. And say this is the correct one that wants to come here, but there's another one floating around, which has some other piece on the end that if it binds on that place, that would be wrong. And so you need some way that you can get the right thing to bind in the right place and the wrong thing not to bind. And you say, well, okay, if the little elements here are different, and the correct thing binds and it fits perfectly, and the wrong thing binds and it fits imperfectly, maybe there's a better energy of binding for the right thing than the wrong thing, which is true, but it turns out that that's not enough. So if you imagine some sort of simple kinetic model where you have this little piece, and it can bind onto this site, and I'll give you an equation for this in a second. And I'm going to be kind of vague about these things, but you have sort of a concentration of the correct molecule, a concentration of the thing it's binding to, and there's a rate at which it can bind, and then it forms a complex, and a rate at which this dissociates. Okay, and what I mean when I write an equation like this is I imagine some differential equation for the concentration of the bound thing, which just says that we bind at some rate that's proportional to the concentration of each of the two things, and then we unbind at some rate that's proportional to the bound concentration. And I'll be writing diagrams like this a fair amount, and whenever I write something like this, this is all that I'm going to mean today. Does this make sense to start? Okay, so what you might want to know is, okay, let's say that all we have is a binding energy, then the rates at which you go from here to here and from here to here are going to be related to some energetics that we don't want to think about right now. Let's just say that these are some rates given to us, and we want to know what is the steady state concentration of bound things in the right place, and you just set this equal to 0 and solve it, and we get something like this. And if we do this with the wrong thing, with D instead of C, then we would do the same thing, but in the end we would end up with the concentration of the wrong thing bound is going to be something like this. Does that make sense? I saw a question. Okay, yeah. Oh, sorry. So I'm maybe using confusing notation here. When this just means the concentration of this thing alone, and this means the concentration of this piece. So this is two different numbers. Concentration of this thing, concentration of this thing, and this is concentration of them bound together. Does that make sense? This here, you mean? Yeah, this is two different numbers multiplying each other. Yeah, good. Yeah, so this is probably confusing notation. But yeah, this is the picture that these are two separate things, and they combine together. Now they're one thing, and this is the concentration of that one thing. Okay, so yes, I am. Good. A big one. Okay, so then the idea for how you would end up turning the things that bind on this spot into a piece of this polymer chain that this extra piece comes off is that you might have some extra thing over here. I think I'm going to use V. That takes this off and to the protein that we're trying to make, and I'm ignoring that now and assuming that this is a very small number, so that we can let this thing sort of equilibrate, set this equal to 0, and look at this concentration and this concentration, and the extra sucking out that we get from here is going to be negligible for now. Yeah. Say it again. Why is it small? Let's just say that it is for now. It doesn't have to be, but it could be. And let's see what happens when it is. I think this is turning off. Oh, got it. Okay. Okay, so then if we think about many copies of this and many copies of C and D, we can ask about the size of a pool of bound complexes where the right thing is bound and where the wrong thing is bound, and we imagine that we have some rate at which we sort of suck them out and turn them into protein, and we can ask what fraction of the time do we get the right thing coming out. So we can just take the ratio of these two, because the the rate at which this comes out is going to be proportional to the size of this pool here and the proportional to the size of this pool here. So you see that the rate of the correct thing divided by the rate of the wrong thing is just going to be C over D times KD prime over KC prime. And let's imagine, for simplicity, the case where the concentration of the right and the wrong thing are actually the same. So these things were being created in a way that didn't know what we needed right now, so it's reasonable to think that they should be in equal proportion. So it's just the ratio of these. So I should say one thing also before I get there. I also have a ratio of KC and KD, right? The non-primes. And I'm going to assume that they're the same thing. So this KC equals this KD, because the primary issue with the rate of binding is going to be finding the spot bind, not about the energy of whether you're right or wrong. And then figuring out whether you're right or wrong is going to be more related to the off rate, whether you dissociate and you fall away very quickly or not. But the actual binding itself is not going to be sensitive to whether I've got the right or wrong thing, because how can I know if I'm right or wrong before I have bound anyway? So I should probably even just write KC here. I'll leave it for K to not. But yeah. Let's assume that they're the same for now also. Yeah. So you end up with this ratio of these falling off rates that determines how good you do. What fraction of the time do you get the right thing versus the wrong thing? And if you look at numbers in biology for what these rates are, you find out that this is about 100. So the error rate should be 1%, but it turns out that the actual error is about 10 to the minus 4. So a factor of 100 smaller than what happens if you look up these numbers and see what we know about them. So there's something weird, and it's hard to do things quantitative in biology. We're starting to get to the point where we can do that now, but we don't even have sort of logarithmic accuracy in our prediction here. So this is really bad. So something is wrong. Something must be going on that isn't what we think is going on. And whenever you see a mismatch on a log scale of what a simple sort of back of the envelope calculation gives you and what you see in an experiment, it tells you something interesting potentially. Does that make sense? So we need to figure out what's going on. How do we do better? It could have been that that biology used chemistry such that these rates were different and were this small if this is what it needs. But that's not what happened. Biology decided to use something else. Okay. So this was the sort of conundrum that led to what is one of the yeah. So this is an observed number, 1 in 10,000 error rate, and also these numbers can also be measured. So if you can measure all the numbers in this, but the left-hand side doesn't equal the right-hand side, something's wrong. So this whole framework must be wrong, is the idea. There must be something else that's going on. Okay. So this led one of the I would say greatest theoretical biologists of the 20th century, John Hopfield, to come up with a new idea, which seems to be the right idea. It's a long time ago. I know this is current topics. This is 1974, but you know, we got to start somewhere. And this is a paper called Kinetic Proofreading. And it's a very, very beautiful paper. It's very readable. It's if you want to learn this subject, it's probably better for you to read this paper than to listen to me, honestly. So go read this paper. I'll do my best to give you an introduction to it so that you can go read it more easily. But since this paper came out, I can't even do math, but 44 years ago or something, it's found application both like in detail and in spirit, in a sense, in many places in biology. And I think it's one of the general principles that has emerged for exploiting physical phenomena to do interesting things in biology. And you know, one of the things that makes working in biophysics exciting is that you get to think about not just what happens when you set up a physical system in some way, but you can think about what that's useful for. So in a way, maybe it's halfway to engineering, but it also can be pretty neat when you find a novel way to exploit some physical phenomenon to do something interesting and useful. And that's essentially what Hopfield has done here. And what he figured out is a way to exploit non-equilibrium physics. So, and this is a subject that probably most of you don't know very much about. Most everything you know in statistical physics. As an undergrad, I didn't know any statistical physics, so if you've taken any, you know more than I know, but probably you don't know any non-equilibrium statistical physics. So I'm going to give you the gentlest introduction that has the minimal amount of math, but hopefully get some of the concepts together. And we'll see how we can exploit aspects of non-equilibrium physics to get specificity and make our error rate go down at the expense of burning energy. So it'll cost us something, but we'll get something, and that's kind of neat, and maybe allows you to think about purely physical systems in this way as well. So the idea is, in fact, I wrote this here, but I should probably go over here to draw the diagram. The idea is, let's start like we did before. Let's have our on rate and our off rate. We bind. And now let's say we're not done. Let's say there's something else that happens. And with some rate m, this bound complex can be altered in some way. The jargon in biochemistry would be something called a post-translational modification. It doesn't really matter what it is, but you're doing something to modify it, the protein. You're tagging it. You're changing its chemical structure in some way. And actually, in this particular example, this process of going from here to here is going to use up an ATP, in fact. And that's one of the reasons why I'm going to draw an arrow forward. I'm not going to draw an arrow back, but there has to be some backwards small arrow. Okay, and let's say from here, now there's this V, which whatever this pool is, sucks it out and takes this piece off and uses it. And let's think about what happens here, except we need one more piece. We need some rate from here at which the whole thing can fall apart. We give up completely. And I'll call that L. And there should be some small, very, very small, in this case, rate of going this way. So now it's a little bit more complicated. Does this make sense? I'm starting to draw increasingly complicated biochemical diagrams that I want to make sure these make sense. So there's three different species of things. Maybe I should have drawn it in a triangle to not have to draw such a large thing from here to here. Yeah. The V. This is similar to this V here that just says that if you have a bound version of C sitting around, there's some rate at which it gets taken up and used into making the final product of the final polymer that you want to make. So you take this piece off and you make the polymer. And in this case over here, it's the same, except this thing gets modified or something like that over here. And then once that's modified, then it can get taken. Does that make some sense? So there are these pools of things sitting around that are bound and ready to go. They're just waiting to be used at the final stage. And V is the small rate at which those things actually get used up. Okay. Yeah. It's a good question. We'll come back to it. So, in principle, so when I write something like this, all I mean is an equation like this, right? And when I write something like this, I have a bunch of arrows that tell me when things enter, when things leave in a differential equation like this. So I could write down some differential equation with parameters here and here, and I'm going to imagine a situation where this one is much bigger than that one, and I'll explain what I mean by that in a minute. And actually, maybe now's a good time to discuss this. But there are in general, if we again live in the world where this V is very small, so we can forget about it for now. We now have 6 different parameters of the model. There's K, K prime, M prime, L prime, right? And you could ask, what kind of relationship do I need between these parameters for the system to have an equilibrium? Let's think about that for a second. Does anyone have any idea how we would find a relationship between these parameters? And so what does it mean for a system to be in equilibrium? Not no rate of change necessarily. You can have changes, but they need to compensate, right? So there's a not that the concentrations don't change, because they can be stationary but still be out of equilibrium. There's something more specific. Yeah, it's more than just a fixed point. I'm looking. This is necessary but not sufficient. There's one term I'm looking for. I think you're getting to it there. Yeah. So the phrase I'm looking for is detailed balance. And what that means is that we have changes going from here to here and here to here and here to here and here to here, and what we want is to have it be such that the number of times we go from here to here equals the number of times we go from here to here, and the number of times we go from here to here equals the number of times we go from here to here, and vice versa for every link on the thing. That's what's called detailed balance. You can have a balance without a detailed balance. So you could have all these concentrations being stationary, but you don't have a balance between those, because now that we have 3 states like this, we could imagine a situation where the dynamics was such that we were going around in a loop like this, and we were cycling. And if you saw the system cycling like this, there's something that tells you that has to be out of equilibrium. Does anyone? There's another term I'm looking for why that tells you that has to be out of equilibrium. There's some sort of principle that's broken when you see a dynamics like that that's going sort of clockwise around a loop like that. Yeah, you need an input of energy, but if you watched a movie of a bunch of particles going from this state to 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 this, like this, and then you watched it backwards, you would see them going like this, right? So that tells you that if you have a cycle like this, you're breaking time reversal symmetry. And if you're breaking time reversal symmetry, you're going to have to be spending energy to make that happen. Does that make sense? So let's write down the conditions for detailed balance. We're not going to end up using this in the end. I just want to make clear. So let's look at, let's say, this one. So here, to have detailed balance, we need the ratio of these k's to be equal to the ratio of the concentration of the bound versus these two concentrations. This is just by this up here and this up here, and looking at the rates at which we go one way or the other, right? Similarly, we can do this for m, and we get that m over m prime has to equal whatever this weird modified thing is, divided by this not modified thing. And and the L's are something like this. So now we have 3 different equations. We can combine them in some way and get a relationship between some of these parameters that needs to hold. In particular, we need m over m prime to equal LC over LC prime times KC prime over K. And when that's true, then we should have detailed balance. But if I tell you, here's a system, I'm going to choose these parameters all however I want, in general, when I solve out all the equations, I'll end up, if I don't satisfy this, I'll end up with some cycling, and the system will be out of equilibrium. So it's some very special set of these rates when the system has an equilibrium. Does that make sense? Yeah. I didn't totally follow that. Say that one more time. Mm-hmm. 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 I didn't totally get it, but maybe we can talk after class about it. Yeah, sure. Yeah. Yeah. And I'm being very casual about this, so I'm being very non-rigorous. But all I mean is that if I look at this process in its steady state, I'm gonna have times where I go from one configuration of the system to another configuration, times when I go from this configuration back, and it should be the case that the number of times I go this way equals the number of times that I go this way. If it's not, if there's a net flux to the right, for example, then across that link, if I played the movie backwards in time, I would see it going the other way, in which case I don't have time reversal symmetry, and the system must be out of equilibrium. Sure. Is there another question? Cool. Okay, so this is just a little interlude about the sort of two main kinds of steady states that you could have in a system that now has 3 different states instead of 2 different states. We haven't said anything about what that can do for you, whether that's useful or not. Of course, what we want is to go back to this question of what does the error rate look like when we now have a system like this running with our correct thing, and then another one with our incorrect, just like. So we want to imagine another situation where we have KD primes and LD primes as well, and there are a couple of just based on what's going on with the chemistry, places where we don't expect there to be any dependence on whether we have the correct or incorrect thing. The first one, like I mentioned, is this K. This is just whether something comes and binds and hits the spot or not, and how could you know? How could the rate at which you hit be related to this one or this one if they're almost the same, and it's just some subtle thing about how well they bind. So let's assume that that's the same. It turns out that these rates as well, going from here to here, something gets changed up here, and it's not really affected by what's going on down here. So this M and M prime are also going to be independent of whether it's C or D. Maybe I should write these things down. So M as well as V don't care. If we have the correct or wrong thing D. The main place where there is dependence is the K, C, and D primes, and the L, C, and D primes. I left it here that this crazy process going from here all the way to here, which is basically never going to happen, has a C on it, but that one also, actually maybe that one does depend on C, but it basically never happens. Okay, so now if we look at the rate of correct and wrong, like here, we need to look at the steady state concentration, not of just the bound state, but of bound with this modification. So if we look at this, now this thing here, if we assume that V is very small, and we assume that LC is very small, and we assume that M prime is very small, we have a source and a sink. We have a source coming from here, and we have a sink going this way. So I'm trying to do this all without having to solve anything at all, trying to give you the simplest regime. But in that limit where this is very small, and this is very small, then this is going to be related to this. And then we can go and relate this back to the original concentrations. And just like we said before, this is going to be proportional. If I multiply it by this v, which is very small, this is going to be proportional to the rate of taking up of the correct thing. Does that make sense? Sort of. Explain this again. This one. The main way in which this is going to be lost is by falling apart completely and going back to the beginning, and that happens with some rate LC prime. So the size of the pool of this times LC prime is the rate at which things get lost. The rate at which we get them is m times the concentration of the thing without the modification. So we have a flux in of things, and then we have a flux out of things, where I could multiply this here, and I'm just equating flux out with flux in. Yeah, cool. Yeah. Say that one more time. I don't think I'm assuming that. Am I assuming that? If I cared about the concentration of these, then that's true. I would need to think about whether I want these to be the same order or much smaller. But if I'm from my perspective over here, the only way in which these can directly affect me, actually this crazy jump going forward like this, and since I'm assuming that this is small enough I don't have to worry about that, then whatever's happening to me over here is only affected by the initial concentrations via this intermediate, which is kind of the pathway that I tried to take to get out to the original ones. Let's see. So someone said what's happening here, and that's flux in, flux out equals flux in for this, and then here we just used what we had over there for this, and I guess it's worth, yeah. So in this case, we are sort of assuming that this is bigger than this. So we're assuming that this equilibrates first, and then once that's equilibrated, then we go through this next process. Okay. So now we can look at the rate of correct divided by the rate of wrong, and you get something like this, which if we assume that the ratio of these rates of falling apart versus jumping into this configuration, if this ratio is similar to this ratio, just for simplicity, then I might say that this is now like KD prime over KC prime squared. And this now gives us our 100 squared. So we got our 10 to the fourth instead of 10 to the 2. So the idea is, instead of letting the system sense some difference in these falling apart rates that distinguish C and D, once we expose it to that chance to fall apart with this factor of 100 difference in rates 2 times. And if we allowed it to do it 2 times, we could get up to something like a factor of 10 to the 4 now. So you could imagine a situation where you had more steps instead of just having one star here, I could have another star, and another star, and another star. And if I had more and more steps in this process, every time I do that, if I did it really well, if I had all these things driven strongly out of equilibrium so that this is stepping forward and not stepping back. So this is all done in the approximation where m prime equals 0. If I could do that, then what I would find is that instead of getting 100 squared, I would get 100 to the n, right? So I could get arbitrary precision with not very good parts just by constructing a network in some way, and then being willing to spend energy on it. So that's actually pretty cool. Here's a pretty simple idea for how you can get very high fidelity specificity and decision making when your parts are not that good. If you're clever and you design the network in some way, and you're willing to spend a lot of energy potentially. Yeah. The corresponding versions of these, but for the D instead. Yeah, I didn't draw the diagram. Yeah, there should be a whole other diagram like this, but for the D, lowercase d instead of lowercase c. Yeah, here I'm assuming that this is sort of similar to this, just for simplicity, to give you a sense of where, we started out with 10 to the 2 when we wanted 10 to the 4. The way that comes about is if this ratio for the K's is similar to the ratio for the L's. It could have been a factor of 10 you get instead of another factor of 100, depending on what the biochemistry is. But yeah. Say that one more time. That's right. Yeah. So every time, if you imagine many steps in this process, you're letting the system have its 1% chance of being wrong or something like that. And then if you pass the next stage, you have a 1% chance of being wrong. And every time it's sort of independent chances. So you sort of beat down. If you do it 6 times and you pass the test every time, it's very unlikely that you were just lucky 6 times in a row, flipping coins every time, right? That's the idea. Yeah, so here, just for simplicity, I also assume that these concentrations were equal. Yeah. Mm-hmm. Yeah, so you're saying, imagine a world where over here, D was more likely to fall off, but over here, suddenly C was more likely to fall off in such a way that this product actually canceled and now I had no specificity. That certainly could happen based on the sort of biochemistry of the kinds of systems that are being studied here. Yeah. Yeah, I'm looking in the sort of section of parameter space where I get the things that I want to get, not all the things that could happen, like you say. And indeed, if you look, maybe that's intuitive in sort of what's going on here for this condition for detailed balance. If I had these rates be, I guess, be sort of opposite, and then I had the m's be equal, then I'd have detailed balance, in which case maybe this is a good thing for you to think about. So if you have the rates such that you have detailed balance and you do all this out more carefully, you'll find that the rate of correct versus rate of wrong is not improved at all. You will reduce back to this at best. So yeah, it's only in certain sections of parameter space that you get this enhancement. And I've focused, to give you 3 lines of algebra on the part where you get the best answer. It's also worth mentioning that here, I shouldn't be allowed to put equal signs here because these are all approximations where I'm setting things like m prime to 0. And if I set m prime to 0, if I wanted to make a physical system that had the ratio of m over m prime being infinity, I need to essentially spend an infinite amount of energy to do that. So I can't really do that. So I shouldn't really be able to put equal signs here, but I'm doing it anyway because it's close enough. And it turns out I wasn't planning on going into this today, but you can compute how much energy is being expended in running this process. If people are interested, next time I could tell you how to do that. But you can compute that. You can compute the fidelity, and you see that there's I don't know if this is generically true, but within the parameter regime that I'm thinking about, as you spend more energy, you get better performance up to this point. But to get this 100 squared, exactly, you need to spend an infinite amount of energy. To get epsilon less, you have a finite amount. But yeah, this is this crazy regime where you're using infinite ATPs so that you go forward and never backwards. Yeah. Yeah, I'm only thinking in terms of probabilistic descriptions of Markov processes. I'm not thinking about kinematics. Yeah. I was not planning on going into more detail. We can. I'm not an expert in this, but I know some things if that's of interest next time. So, in the remaining 25 minutes or so, what I wanted to do was give you some more modern examples of this kind of this idea where you want some performance. The performance doesn't seem good enough if you just measure the quality of the parts, but if you inject energy into the system, you get better performance. And I'm going to start erasing things. Cloth is better. Before I do, are there any more questions on kinetic proofreading? So again, you should read this paper by Hopfield. It'll do a better job of explaining things than I have. And I think especially after this sort of gentle introduction, it'll be pretty easy to read and exciting. Any paper by Hopfield is worth reading, essentially. Okay. So the problem that I wanted to think about, there's two. The last one, if I get to it, will be something that I actually did. But there's a recent application of kinetic proofreading in the field of immunology that I just wanted to give you a flavor of that I think is pretty exciting. And in immunology, there's a similar kind of problem. So I actually did not remember to write down the reference, but the authors are Paul Francois and Alton Bonnet. If you want it and you can't find it, let me know. And the idea is you have these cells in your immune system called T cells. And they need to look at little chunks of things that are either yourself, little chunks of proteins that belong to you, or things that are non-self. They belong to some pathogen that this thing needs to recognize and turn on some program to attack the bacteria or whatever. And the receptors are set up such that, let's say the foreign thing binds for 3 seconds. But there are very few chunks of foreign stuff, and there's a ton of self protein chunks. And the self stuff binds for a very short amount of time, maybe 1/10 of a second. But the problem is that there's much more of it. There's so much more of it. So how do you possibly find these rare times when the foreign thing binds for longer, when you have this, massive population of self stuff that's nonetheless binding for about an order of magnitude less time? So yeah. Say it again. Yeah, so you want this cell, which is called a T cell, to gain confidence that it's detected something foreign, and then tell its superior, do something, send some signal to turn on some program to start attacking something. But this is just trying to figure out whether there's a reason to turn on that program or not. And so what you would like, and what seems to be kind of the case, is if I plot, even like on a log scale, the binding time in seconds versus the called the concentration, or maybe the number of things per T cell, 1, 10, 100, 1,000. What you see is a sharp delineation that looks kind of like this. The idea being that if you bind for long enough and your concentration is high enough, I want you to respond. But if either of those things are not true, you shouldn't respond. So the foreign ones, which bind for say 3 seconds and have a low but high enough concentration, will sit somewhere like there. But the self ones, which bind for a very short amount of time but are very, very high density, will sit somewhere like here, and we won't get a response, right? So this is what you might like to happen. It turns out that if you think about using something like kinetic proofreading that we just talked about to solve this problem, you end up with a curve of response versus no response that kind of looks like this, and it's not good enough, it turns out. So while kinetic proofreading is maybe a useful idea, it's not enough. And if you live in a world where you have short binding times but very, very high concentration of self molecules, this kinetic proofreading sort of boundary will be such that you'll respond to self. You'll get autoimmune diseases all the time. So kinetic proofreading can't work for this. And what these authors figured out, Paul Francois is a theorist at McGill. They figured out a really neat way to modify kinetic proofreading to get a response that looks approximately like this. And I wanted to just give you a flavor of what that looks like. I'm just going to draw the diagram of the interactions. Hopefully it'll be intuitive that, oh, that's an interesting idea, that kind of works. And you can look at a diagram of chemical reactions that, you know, maybe an hour and a half ago looked like some annoying network of things that it's just a bunch of chemistry. Now you can give logic to it and say, oh, this is doing that and this is doing that, and you can piece together modules and you can see how interesting computations are being performed by this network. So the idea is that, let's see, how should I draw this? So we have these receptors and they can bind. So we have a state of sort of the molecule, which I'm calling a ligand, and the receptor next to each other, and they can bind. And then the receptor can get a modification like in kinetic proofreading. Exactly what that is doesn't matter. And in fact, these receptors, it turns out, have many different chances to get modified. They get these weird tags multiple times, but let's just draw two of them. And in kinetic proofreading, we had sort of this on rate, this off rate, we had this step forward, and then we had this response. And that wasn't enough, we had said. So what Paul realized is, let me call the C naught the concentration of bound receptors. It turns out that on these T cells there are many, many, many receptors. And then there's stuff inside the cell. And inside the cell, there is a thing called K, and K itself can get some modification. And it turns out, hopefully I can draw this in a way that makes intuitive sense, that when this thing is bound, it helps the K go to K prime. So it catalyzes the reaction, making K go to K prime. Does that make some sense? And it also turns out that this K catalyzes the reaction going from the bound receptor to the modified bound receptor. The K, actually. You want it to be this one. So if I can explain what's happening, so remember, this is happening, there are many, many, many receptors all around the cell, and they're all talking to one pool of these K's, K primes. So what's happening here, there are many, many versions of this top diagram for every individual receptor, but this bottom piece, the concentrations of K and K prime, is shared amongst all of them. And what happens is that if you have a self thing, you end up binding to a lot of the receptors at once. And what that means is that you have a lot of these bound, and those are helping make the K's go to K stars. I keep saying prime, but I'm writing stars. So a lot of the K's are now in K stars, and then that makes it harder to go from here to here because you need the non-starred K's to go forward. So it's sort of adapting the system away and saying, well, if there's a lot of you around, I'm going to make the game a lot harder for you. Whereas if you're a non-self, if you're foreign, and only one or two bound, then almost all the K's are in the non-star form, and the rate at going forward is much higher, and then you have a higher chance of ending up with a response. Does that make some sense? So I don't want to go through the math. I think it's a PNAS paper from maybe 3 years ago by Paul Francois. And Alton Bonnet is an experimentalist who has done a lot of really amazing work showing that this idea, while very, very simple, does seem to be what's actually going on in these T cells, and is really important for how they work. So it's a pretty neat example of taking an of kinetic proofreading, adding in an adaptation module, if you will, and then getting something new out, which is this sort of very, very sharp response curve. And it's I think, you know, we're entering a stage of thinking about theoretical problems in biology where you can start adding in together modules and producing certain kinds of computations that are really non-trivial and fascinating, and where you try to understand what existing processes in biology are doing. There's also a growing world of synthetic biology where if you can dream it up and you can imagine some network of chemical reactions that does something really, really neat, there's someone that can build it for you, and then you can actually, you know, make a cell that will do something crazy. That might be good, it might be bad, but whatever. So yeah, okay. So does this make sense? I think I have time to give you the last example. So I was going to move on to my final example. Okay, so the last example is sensing an external chemical. If you're a cell and you're in a developing organism, you need to know where to go. If you're a bacteria, you want to figure out where food is. There's all sorts of reasons why you need to be able to sense chemicals in the world around you and do something with that. And this is a very, very old problem, originally considered, I think, by Berg and Purcell. I'm not going to go through that in the 70s. And I just want to give you a 5-minute summary of my contribution to this from a couple of years ago. This is a paper by my collaborator Pankaj Mehta and me in PNAS from 2012. And essentially what we realized is, imagine you have a cell and it has some receptor and it detects some chemical. The chemical binds to the receptor, it unbinds, and when it's bound, maybe it changes the conformation of the receptor, and that causes it to signal something inside the cell that, oh, there's something around. People have studied the physics of the receptor for many years, and they've thought about, imagine a time series. If you're the receptor and you're getting bound, and then you're unbinding, and everything is noisy. There's individual molecules. I can't think at the level of concentrations necessarily. I've stochastic events where the thing binds and unbinds. So an actual individual receptor, this is a silly graph, but this is time versus bound, unbound. You get a sort of telegraph noise of binding and unbinding, and you get to observe this process of binding and unbinding for some amount of time, and you want to then, from that time series, infer the concentration of the chemical. And the way you would do that is similar to what we had before. The on rate is going to be concentration dependent. It's going to be proportional to concentration, and there's some off rate. And you can imagine in some steady state, the fraction of time that you're bound, you just solve the differential equation like we did in the beginning of the class, and you'll see that the fraction of time you're bound is related to the concentration, right? So if I could compute the fraction of time that I'm bound, then I can estimate the concentration from a time series if I'm a single receptor. It turns out that that's not the best thing to do. It took 30 years for people, or maybe even longer, for people to realize this, but Ned Wingreen at Princeton realized that if you imagine a process where you have these binding events and these unbinding events, and you have it such that the on rates are the ones that have concentration dependence, but the off rates are just some off rate, then this noisy process binding and unbinding and binding and unbinding, the time that you're bound is going to be stochastic, right? Sometimes it'll be short, sometimes it'll be long. And there's no information about the concentration in those intervals. So it'd be better if I could ignore those and get rid of them and only look at the duration of the unbound intervals while I'm waiting for something to bind. And it turns out that if you do that, that's equivalent to what's called maximum likelihood in statistical estimation, and you can do it, and you do twice as good as what people thought for 40 years was the best that you could do. So this is just an aside to say that it's intuitive from what we were talking about before that the steady state sort of fraction of time that I'm bound has information about the concentration, which is true, but it turns out that if you're smart, you can do better in terms of your uncertainty in your estimation of the error if you take the noisy process into account. I'm not going to go there today. I just want to think briefly about how a cell inside would estimate the concentration or the fraction of bound time from a time series like this. And the reason I'm bringing it up in today's lecture is if you think about it, there are two ways to think about it. If I'm at some time here, let me take a different approach to this. So if I have some internal network that is going to do something like time average a signal, and I want it to be working in the steady state, I need to be able to reuse my parts over and over again. I need to be able to perform some computation and then reset it, and perform a computation and reset it, and imagine a dynamical system that's doing this in continuous time, that's sort of constantly resetting and performing this computation at the same time. And if you're going to make that happen, the process of resetting, it's been debated for 50 years, but it's pretty well established at this point. There's something called Landauer's principle from early 1960s, that every time you erase one bit of information, it should cost you kT log 2 of energy. You want to have a process that is inside the cell that is computing some concentration like this by time averaging the signal. It should cost you energy, and to run it in steady state, you should have to burn ATP. So any network that you construct to do it should be out of equilibrium. And I'm not sure if it's worth it for me to draw what we did. I guess I have a couple minutes, but so the idea is, let me zoom in on this little piece of the membrane and imagine that I have my receptor that can be in two configurations. Actually, let me make it simpler. Let's say I can be unbound or I can be bound. And when I'm in the bound state, let's say that I have an internal dynamics. I have some protein X, and X is transitioning between being modified and not modified. As you can tell, a theme from today's lecture is that all sorts of information processing at the level of chemical computations is being done by making modifications on proteins that I'm not really saying what they are. But all this biochemistry that might sound really boring is actually doing interesting information processing. So this X can get turned into an X star at some rate when I'm not bound, and it can get turned into an X star at a different rate when I am bound. I'm not going to give names to the other things. So if I imagine what the what the network of interactions between states looks like. I'll try to draw this schematically. I have a world where my receptor is off and it's not bound. I have a world where my receptor is bound and on and doing something different. So the only difference here is that the rate at which we turn X into X star is modulated by whether we're bound or not, and presumably when we're bound, K on is bigger than K off, so it makes more X's go to X stars. So we can have a world where we have different number of X stars. And we have a world where we have the receptor being bound and on or unbound and off, and we have transitions between all of these things. And we said that when we're in the on state, going from X to X star is big. So these have K ons and these have K offs. So you can imagine that what ends up happening, if K on is bigger than K off, you end up with sort of cycling that's going on in all these loops. And with some some concentration out in the external world, that leads to maybe way down here, some average number of X's turning into X stars, maybe not 2 or 3 or 4, but 1800 or something. But that it's sitting there around that 1800 value, and it's stabilized there by this cycling that sort of, when you're on the upper track of the ladder, you go to the right. When you fall off onto the lower track, you go left, but you sort of hang out at some place, and then you can read out effectively what the external concentration is based on the number of X stars that are inside of the cell. But you can see, because you have this cycling, that you have to have the system out of equilibrium and burning energy. And we made a plot. If you imagine, call the difference between this K on and this K off a delta K. If you imagine plotting the power consumption, which you can compute, when delta K is 0, when there's no difference, there actually is no cycling, and the power is 0. And as you increase delta K, it goes up. But if you imagine also plotting your uncertainty in the concentration out in the world, when delta K is 0, you're not incorporating any information, so this actually diverges, and then it decreases as you spend more energy. So there's you see that as you spend energy, you reduce your uncertainty. And this is another sort of general principle for using energy in biology. So these are all examples of how, if you think about what's going on in the biological system from the perspective of what the system needs to do, you can find some internal logic to how it works, and there's interesting physics along the way as well. There are a lot of interesting questions in non-equilibrium physics that I'm ignoring in this lecture, but it leads to all sorts of questions where you can even study fundamental physics with no connection to biology if you so desire. So yeah, I think I have about 10 minutes. Maybe I should stop and take questions. In the subsequent lectures, I'm going to leave of cells. I'm not about proteins or cells, anything like this anymore. And I'm incredibly abstract and talk about general principles of biological function at larger and larger scales, in a sense. And we'll talk about information theory and all sorts of other things. So yeah, are there any questions about this stuff? Oh.
So I have two questions.
Yeah.
Naively, I would think that if you want to estimate the concentration of your like ball agent, you just measure the average time that it is bound to your cell. Why isn't it correct?
That will give you the right answer. It's just not the most efficient answer, in the sense that So maybe my writing is too small here, but if you imagine this process of particles in the environment binding and unbinding, every time they bind, that binding rate is proportional to the concentration. Every time they unbind, just physically, they just fall off at some rate. There's no concentration information in the falling off. So the noise in how long they stay bound is just added noise that if you could ignore it, you would probably be able to get a better estimate. And it turns out that that's true. And if instead of looking at the average time bound, you look at the average duration of the unbound intervals, you get with a finite sample. So you don't have infinite time; you have a finite amount of time to measure. And if you look at your error bars on when you do an estimator that's based on the fraction of time you're bound, and error bars when you look at the average duration of unbound intervals, which is the more complicated one, you find that the error bars are half as big in the latter case. So you can, while both of them are centered around the correct answer, with a finite sample, you can do twice as good in terms of your uncertainty if you do a more sophisticated thing.
Another question: why the name proofreading in kinetic proofreading?
Say it one more time.
Why the name proofreading in the?
Because you're trying. So if you're proofreading like a paper, you're looking for typos or errors or something like that, and this is just trying to make sure that you don't make errors. So I guess you're right that rather than proofreading, you should think of it as typing very carefully without making errors to begin with.
Okay, thank you.
Sure.
In that graph, it was determined experimentally or something like this. The response, the area, the place where it is, where is response and where is not.
So I think these kinds of graphs are very difficult to come by experimentally. There is experimental evidence that the systems that they were studying look somewhat like this very, very sharp boundary, almost infinitely high. But you would need to do an experiment with sort of every different concentration and ligands with different binding times. So I think mapping out this diagram very precisely is very hard, but the evidence that we have indicates that it's something very, very much like this very sharp boundary.
Thank you.
Yeah.
I have two questions. The first one is to clarify that diagram is like a more complex than the other ones below, right? I mean, you're saying that instead of just going from X to X prime, you get other stages, and so your network gets more complex, and so you have that processes over there.
So what I mean here by having 0, 1, 2 is that it's not that X prime or X star becomes X star star and X star star star. I just mean like the number of X stars. Imagine a big soup of X's. There's 10,000 X's, and this is how many of them are starred.
Okay. And the other question would be, regarding the Landauer principle that you just tell us as well, is it like when you turn off or you unbind that molecule, you're erasing information I mean, you're resetting your machine. I mean, when you reset that machine, which is inside that cell, then you are losing that information, and that erasure of information is what provides or gives that effect of increasing the heat there, and that's why you're saying there's a non-equilibrium process. I mean, that's like the physical sense behind it.
Yeah, exactly. Yeah, that's essentially, that's right. I've forgotten the exact statement, but there was someone who wrote a follow-up paper saying that the network that we considered can't actually hit the Landauer bound because I forget, it's like working at fixed chemical potential instead of fixed particle number or something. But it can get within like a factor of 3 of the Landauer bound, which is certainly better than modern computers that we have now. So it seems like a relevant idea.
Hello. I was thinking, how do you assert this process? For example, in this Francois Alton Bennett, how you said that this was a model, but how do you assert that this happened? How is the experiment? How do you get the data of the energy of the K and K primes to get that 100 or 10,000?
So those numbers from Kinetic Proofreading, you should go read Hopfield's paper to look up where he gets those from. This stuff on the T cells is very modern and to some extent is work in progress, and checking that this idea is what's going on is not easy. And they have like 5 or 6 papers that, if you want to go into the details, there's a lot. It's definitely beyond what I want to talk about today, but you know, in lots of areas of science, you know, having the idea is the 1% part, right? And then you need to spend a lot of effort trying to test whether it's actually what's going on in a real system.
Yes, because from what you said, there is a theoretical part in biophysics, but there is essentially an experimental one.
Absolutely, yeah.
And how do you make these graphs, or how do you see this behind process that because normally in biology you see the reactions or the chain processes, but the math that happens behind is not something so clear to see, I believe.
Yeah, I mean, making that connection is very difficult, and in any particular system, it requires a very close collaboration between experimentalists and theorists. In my own personal experience, when I collaborate with experimentalists, I like to go to their weekly group meetings when I can, really know everything I can about the details. You know, you're analyzing, you know, almost raw data that comes out, so you really know exactly what's going on. I'm kind of minimizing that aspect of the work in these lectures, mainly because it's easier to get, you know, access to information on doing biological experiments. It's sort of harder to get access to thinking about theory in biology. So I'm focusing on that, but I don't want you to come away with the impression that you know, all you do as a theorist is like sit back in your reclining chair and have an idea and let someone else sort of figure it out. The bulk of the work is trying to connect the idea that you have to data and figure out what, not just have an experimentalist come to you and say, here's my data, do stuff with it, but actually say, okay, if this is the mechanism that I think is at work, how do I distinguish that from a different one? What kinds of experiments can I propose to the experimentalist that would help me delineate between this and other things? And that's where a lot of the thinking comes in.
Thank you.
Sure.
I actually have 2 questions. The first one is about what are the time scales for the usual binding time and the scale in which the bacteria or something is actually observing. Because I imagine it has to make a decision rather quickly.
Right.
So it can, I imagine like 10 seconds would be too much to observe that and then make a decision. So what are the order of magnitude?
So I don't have offhand the time scale for the on and off fluctuations here, but around a second is how long it makes a decision. Yeah.
The second question is about, you said that looking at the unbound time is more efficient because the cell has a limited time to analyze its data. Is it always more efficient because the time is limited, or is there a natural scale in which looking at the binding time becomes actually just the easiest and most efficient process?
I think from a statistical perspective, looking at the unbound intervals is always better. The bound intervals have no information in them. However, I should have mentioned this and I forgot to. If you want to look at just the unbound interval duration, you can show that if you're going to do that, your receptor or something very close to it needs to be out of equilibrium. And you actually have to spend more energy to perform that computation than the computation where you just do the time averaging. So there is a trade-off there that it's more difficult to compute and requires more energy, in fact.
In the kinetic proofreading, you reached an equation that I don't understand how you got there. It was the bracket CC bracket star equals bracket CC bracket M over LC prime. How did you get that? What did you assume?
Yeah, I can show you that really quick. So I think we had
A star? Okay.
we had this process, and then we had this thing was falling off to this, right? And I think all that I had said was the rate at which stuff comes into this is this times m, and the rate at which it goes away is this times LC star. I just equated those two.
And then put it on the equilibrium. Okay.
Does that make sense?
Okay, makes sense.
Cool. And of course, there are this backwards process. There's this one, and I'm just saying all those are small enough that we can neglect them. Yeah, think of that of this like a differential equation that I'm in the steady state of. Exactly. Yeah.
In the immunology example, I didn't understand well why this mechanism of catalyzing the process to get less K and then like having less this transformation for the star state. I don't understand well why this explains, or if it explains the graph of response and binding time.
So I didn't go through the process of how this gets you to something that looks exactly like this. I just wanted to give you the general flavor that that it's adding in this extra piece down here where you have this population of Ks inside the cell, such that the Ks without the star move the process forward, and the Ks with the star are sort of sequestered and not allowed to do anything. Adding in this extra module makes it more difficult for ligands that are at high abundance. The reason being that means if you're at high abundance, you'll have many of the receptors that are bound instead of unbound around the cell, and then when you have that, you'll have a high concentration of this C0, and then that will encourage the Ks to become sequestered, and then when they're sequestered, it makes it that much harder for them to move forward. So by having a large population of self molecules, they make progressing along this rightwards along this path harder for themselves by having so many of them. And that's going to make it less likely to have a response at a higher concentration. So it's going to sharpen up this curve to some extent. Yeah.
You mentioned there are like infinitely many modifications you can do to these receptors, right? You can go on forever with
not forever, but there's
a lot of them.
One, yeah.
Yeah. Do they all interact with the same K, or are there like many different K things doing this job?
Yeah, the idea here would be that it would be the same K. Yeah.
Okay.
Okay, so let's thank David again. So we start at 11:30, and there should be food upstairs.